Hi everyone, in this video we're going to learn about the Doppler effect, the difference between Redshift and Blueshift, and formulas so that we can use these concepts. So let's start by explaining what the Doppler effect is. So let's look at the famous ambulance example, and what that's saying is if you ever notice when an ambulance is approaching you, you'll see that the pitch is a little higher, and then when it leaves and goes away from you, you'll notice that the pitch gets a little lower. And let's look into why that's happening, and that's through the Doppler effect. So let's read this first. The Doppler effect, also Doppler shift, is a change in the frequency of a wave in relation to an observer who is moving relative to the source of the wave. So moving relative to the source of the wave could also mean that you're not moving, you're staying still, but the source or the ambulance is like moving by you. That means you're kind of moving relative to the ambulance. And this can happen with light, sound, ripples in a pond, etc. Anything with waves. So why does this shift or change in frequency happen? Let's look at it visually. So let's say we have an observer over here. If we have a stationary object, let's say this orange object is what's emitting the light, sound, what's emitting the waves. In a stationary object, it's going to emit the waves at a constant time period. So this is the first wave, second wave, third wave, fourth wave. And it starts from here. It starts from here and it goes outwards. Like if you drop a pebble in a pond, it's going to ripple outwards. Now let's look at if the object is approaching the observer. So initially, let's just say it starts at the center of the circle and then it moves to a final position right here. So from when it's at the center of the circle, it's going to emit a wave that's going to eventually go all the way. It's going to expand by the time the object comes here. So that's the way I think about this one. As the object moves, it creates a wave here first, and then it'll create another wave here, and then another wave here, and then another wave here. And this wave expands to this big one. This second wave expands to this one, and so on. So as the object moves, you'll see that the wavelength gets smaller here, 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 and here, which is what the observer sees. So the observer sees that the wavelength is smaller than what it actually emits, what it actually should be. With the same logic, if we just look at this backwards, we'll see that when the object is leaving the observer, is going away from the observer, here's where the wavelength decreases. So the observer, which is on this side, will see that the wavelength increases. These wavelengths are longer than what it actually should be. So this is how you can kind of see the stretch in the wavelength. So a stationary object just emits a constant wavelength. An approaching object, the wavelength shrinks. And then when the object is leaving, the wavelength stretches. That's why when an ambulance is approaching us, we hear higher pitch because the wavelengths are shorter. And when an ambulance is leaving us, we hear a lower pitch because the wavelengths are stretched. Before we move on, I just want to do a quick clarification on how the universe expands, just so we're on the same page. The universe does not grow like here and then it'll go here. It won't increase from one side. What it does, let's say this is the universe so far, it's literally going to expand like this. And everything is going to grow at once. So if a star is, let's say here and here, these stars won't stay at the same distance. Eventually, the distance between them is going to grow apart as well. So if that makes sense. It's like if you take a stretchy ruler and just stretch, holding both ends of the ruler, you'll see every tick mark in between. All of those are going to stretch as well. So that's how the universe expands. It doesn't just grow from one end. Every space in between, all objects are moving apart together. Now let's move on to redshift. So redshift and blueshift is basically the concept that we were talking about here. So redshift is when an object is receding, so that means going away from us, it's leaving. And blueshift is when an object is approaching. So that's this is going to be blueshift. So the wavelengths can be blueshifted or redshifted depending on which direction they go. And in space, do things usually redshift or blueshift? Well, let's think about what we were just talking about above. the universe doesn't just grow from one side. Everything stretches at once. Everything goes away from everything. So in space, things usually redshift. Redshift. But there are exceptions sometimes, especially in the Olympiads, in the astronomy competitions, when you see problems. Keep in mind that there may be times where things blueshift or approach each other. That's possible. So now how do we calculate redshift? So redshift, which we'll hold as z, we can calculate this using the wavelength observed that we receive minus the wavelength emitted divided by the wavelength emitted. So that's basically the change in the wavelength from when it's emitted to what we see divided by what's actually emitted from the source. So this formula is how you find redshift or blueshift. Now, relativistic redshift, you use this formula if you know the wavelengths, but if you know the velocity of the object, if it's approaching or receding, this is what you use. Z equals square root of 1 plus v over c divided by 1 minus v over c, and then on the outside we just have a minus 1. So this is how you would calculate the redshift. If you have velocity in meters per second, you'd put that here, and then the c, that's the speed of light. That's a constant. It's always 3 times 10 to the power 8 meters per second. That's the speed of light. Let's move on. Now, what if you have z in a problem? You have the redshift, but you don't have the velocity. You need to find that out. This is how you would manipulate the equation above to find, to isolate for v, basically. So we start out with z equals square root of 1 plus v over c, then 1 minus v over c, minus 1. The pretty obvious first step is to bring 1 over to the other side and square both sides to get rid of the square root. So we have z plus 1 squared equals 1 plus v over c, 1 minus v over c. All I did was bring the 1 over and get a plus 1, and then I undid the square root by squaring both sides. Now this is the tricky part. There's a property that goes like this. If I have a over b equals c over d, I can write another true statement, which is a minus b over a plus b equals c minus d over c plus d. This is also true if I know this. So we can use the same identity on our equation here. And how we do that, we think of an imaginary 1 in the denominator. And then we can do the a over b equals c over d. And let's see how that makes our life easier. So I have z plus 1 square. So this is the a minus the b. So that's 1. And then I'm going to do a plus b on the bottom. Z plus 1 square plus 1. On this side, what do I have? I have 1 plus v over c. So that's basically the c in this equation. And I'm going to subtract 1 minus v over c. And then in the bottom, I'm going to add them. So I have 1 plus v over c plus 1 minus v over c. And how do things clean up? Let's distribute the negative. So that means I would have a negative 1 plus v over c. So that means this 1 and this 1 cancel out. Then I have v plus c, v over c, and then minus v over c. So that cancels. So I'm basically left with 2v over c divided by 2, which I can just write as v over c. So let's rewrite this. I'm going to switch the two sides. So v over c I'm going to put on this side. V over c equals z plus 1 square minus 1 z plus 1 square plus 1. And this right here is the formula that you use when you're given v, or you're given z, you're given the redshift, and you need to find the velocity. Where in the formula before, you can use this if you're given the velocity and you need to find the redshift. And all you do here, you just bring the c over, the speed of light, and just multiply the other side at the 3 times 10 to the power 8 meters per second. So that's how you do that. The alternate version for the relativistic redshift formula is going to be v over c equals z plus 1 square minus 1 and z plus 1 square plus 1. Now you might be wondering which one is more important to remember. I'll say both of them because I've seen both of these show up, especially in the astronomy competitions. almost an equal number of times. This one, memorize this for sure, and then just know this basic derivation so that you can easily find this. Then all you have to do is just memorize one equation and just have an idea of how to get to this one. Or if you want, just memorize both. Up to you. But let's move on to some example problems. Here it says a spaceship is moving directly away, okay, so redshift, from Earth with a speed of v equals 0.8 c. That means 80% the speed of light, where c is the speed of light, yeah. The spaceship emits a signal with a wavelength of lambda e, so I'm guessing that's emitted, equals 500 nanometers. Nanometers is 10 to the power negative 9. Calculate the wavelength emitted of the signal as observed on Earth due to relativistic redshift. Okay, so here's what I'm thinking. I'm thinking, since we're given the velocity, we can figure out the redshift using this formula. And then since we have to find, we're given the wavelength emitted, we can use this formula because we'll have z by then. And this is given to find out the wavelength emitted. So let's start working. We have z equals square root of 1 plus v over c. I'm just going to plug in v right away. It's going to be 0.8 c over c. Then 1 minus 0.8 c over c minus 1. So that means z is... These c's cancel out, right, from the top and the bottom. We have 1.8, 1 plus 0.8 on the top. And then we have 1 minus 0.8 on the bottom. Minus 1. So what is 1.8 divided by 0.2? It's going to be 9. So square root of 9 is just 3. 3 minus 1. We're going to have a redshift of 2. You can just do that in your calculator as well to check. Now, since we have a redshift of 2, now we can use this formula, lambda observed minus lambda emitted over lambda emitted. And we have the redshift. I'll just write this like this. 2 is our redshift equals lambda observed, that's what we have to find out, and emitted they gave us, it's 500 nanometers, which is 10 to the power negative 9, divided by 500 times 10 to the power negative 9. Okay, now if we isolate for lambda observed, we have 2 times 500 times 10 to the power negative 9 plus 500 times 10 to the power negative 9. And if you add this, this is 1,000, this is 500. So 1,500 times 10 to the power negative 9. We can also write this as 1,500 nanometers. And that's our answer. That's our final answer. So this is the wavelength that was observed on Earth due to the redshift. So because the spaceship was moving away, the wavelength stretched from 500 nanometers to 1,500 nanometers. Hopefully that gives you a sense of how significant redshift and blueshift can be. To review, we covered Doppler effect conceptually and what it means when it's approaching or leaving. We covered the difference between redshift and blueshift, and in space things usually redshift. We went over the formula if you have the wavelength. Then we also went over the formula if you just have the velocity. Then we had a formula where if you're given the redshift, how do you find the velocity? And then we did an example problem that has both formulas. We used both formulas of the redshift. Thank you for watching, guys, and I'll see you in the next one. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.